Good morning. This is Nigel Wilson, faculty member at MIT in Civil Environmental Engineering, and I'm going to be giving the webinar today as part of the Bus Rapid Transit Center of Excellence led by Católica University in Santiago. The topic today is making use of automated data collection to improve transit effectiveness, and I look forward to having interaction with you as we go through the next hour. In terms of the I'm just trying to get this. In terms of the outline, sorry about that delay. In terms of what I'm hoping to cover today, I want to go through some topics that many of you are already familiar with in the first 20 minutes or so, talking about the automated data collection systems that the methods we'll be talking about later on are based on, the transit agency operator functions, how these functions are already being affected by these data collection systems, and talk about where we are now, and then in the second half of the talk, give some examples of recent research that we at MIT have been doing in London. The examples I'll talk about are the use of ADCS for origin-destination matrix estimation, the use for measuring service reliability in both high-frequency and low-frequency services, and finally train load inference. I'd like to stress at the beginning that the methods that I'm talking about should be applicable to a wide range of public transport modes, including bus rapid transit, but also more conventional bus service and rail services of a whole range. In addition to MIT's role as part of the Center of Excellence, which is sponsoring this webinar, I lead the Transit Research Program, which has a research relationship with London and Boston, and also we've just started a new relationship with MTR in Hong Kong. So I look forward to giving you some examples of what we've been doing in London as examples of the general class of methods that we're talking about. So to start then, I'd like to talk about the transition that transit agencies have been making over the last 10 years from reliance on manual data collection systems towards automated data collection systems. And I've listed here in the slide some of the key differences that I see between the manual and automated data collection systems, including capital cost, where automated data systems have relatively high capital costs compared with manual systems, but provide a tremendous advantage in having very low marginal costs. Once you've acquired the technology, you can gather data very inexpensively. This gives you fairly easily very large sample sizes once you have these systems deployed, and gives you more detailed disaggregate data, albeit of a limited nature, principally count type data, compared with the more aggregate information one got from manual data collection. I would say manual data collection systems have tended to be somewhat unreliable. They're subject to manual foibles, if you like, whereas automated data systems do have errors and biases, but we can estimate these and correct for them because of the very large sample sizes that we can gather. So as a result of this, automated data collection tends to give us a fairly ubiquitous picture of the aspects of the system we can measure through these systems, compared with fairly limited spatial and temporal picture we've traditionally had from manual data collection. Another important attribute is the availability in real time or quasi-real time, if you like, things that may not be immediately available but are available very, very shortly after their collection, some of the data from automated data collection systems, as opposed to often long lead times in coding and making available for analysis manual data collection. In terms of the systems we're talking about, there are three principal classes of systems. Automated or automatic vehicle location systems, AVL, in which the location for buses is principally based on global positioning systems, train tracking based on track circuit occupancy for rail systems. Typically, AVL systems, although not always, are available in real time off the vehicle, and so they're a very important underpinning for real-time applications in particular. The second class of systems are automatic passenger counting systems, which in buses consist of sensors and doors with channelized passenger movements, which count the numbers of entries and exits through each channel, and then are stored typically on the vehicle. For rail systems, passenger boarding and perhaps alighting counts for stops and stations with fare barriers, and increasingly important in more modern urban rail systems, train weighing systems, which can be used to estimate the number of passengers on board a particular car. These are traditionally not available in real time off the vehicle, although that may be changing in the future. And the third class, in some ways the most interesting, are the automated fare collection systems, AFC systems, which are increasingly based on contactless smart cards with unique IDs, which provide entry information onto individual passengers into the system, and in some cases exit information as well. Again, these are traditionally not available in real time, although in the future that might be changed. So those are the three classes of system which collectively can give us a much richer picture of what's happening throughout the system than the manual systems we've relied on. So the potential of automated data collection systems are to support an integrated database or data warehouse of much information that's been happening in the system, describing what's been happening in the system over a long period of time. Using this, we can expect to develop models and software to support many agency decisions based on the ADCS database. This potentially can put us in a much better position for making a whole range of decisions in the agency, from vehicle control decisions, operations control decisions, up to more higher level management decisions with a pretty solid database to support us. So we can again have a potential of providing insight not only into normal operations but special events, unusual weather, etc., things that we could never dream of really capturing good data on with manual data collection systems, because of the low marginal cost of data collection with these automated systems, we can gather information on a whole range of normal and atypical conditions. I think another very important potential is to provide large, long time series disaggregate, i.e. individual customer panel data for better understanding of travel behavior. We can talk about that more as we go along. The reality is a bit different. Most of these automated data collection systems have been implemented independently over a period of years, not generally at the same time. And for most of these systems, data collection is ancillary to the primary function, which in the case of automatic vehicle location is emergency notification and stop announcements often. For AFC, the primary function is fare collection and revenue protection. So when we want to use this wealth of data for analyzing systems performance, there are many problems to overcome, including the fact that it's often not easy to integrate this data in a single large data warehouse, and it can require expertise and resources that may not be readily available within the agency. I'd like to shift now to talk about the principal transit agency or operator functions that we might look for support from these systems. I'm distinguishing here between the offline functions, which include service and operations planning, SOP for short, and performance measurement. And I've listed here some of the functions under service and operations planning: network and route design, frequency setting and timetable development, and vehicle and crew scheduling. And under performance measurement, measures of operator performance against the operations plan and measures of customer from the customer viewpoint. These are very important functions which do not rely on access off the vehicle to the data in real time, as opposed to the real-time functions. The principal two that I'll talk about are service and operations control and management, which deal with the corrections of the operating plan in light of the disturbances or unexpected events that will incur, and also changes in demand that were not anticipated. So that's the first real-time function. The second real-time function is customer information, where information on routes, trip times, vehicle arrival times are provided to customers. And we can think of these as both static, which is based on the operations plan, and dynamic, which is based on the current state of the system as well as the operations plan. To summarize some of the impacts that we have seen or are beginning to see of the automated data collection systems on these functions, on service and operations planning, automatic vehicle location systems have enabled us to have a very detailed characterization of route segment running times, which enable us to develop more accurate timetables and schedules, vehicle running time schedules. In terms of APC, we have detailed characterization of stop activity, boardings, alightings, and in many cases dwell time at each stop. And with automatic fare collection systems, detailed characterization of fare transaction for individuals over time, which enables us to have a better characterization of traveler behavior. Impacts on performance measurement or performance monitoring, automatic vehicle location, I would argue, for the first time has really enabled us to support on-time performance assessment, which has always been very important, but we've very seldom had large enough sample sizes to be able to reliably describe service reliability and on-time performance. And AFC, which supports more passenger-oriented measures of travel time and reliability. For instance, if you tap when you get into a rail system, you tap when you get off a rail system, then you characterize the individual journey time and the reliability of that journey time by looking at a sequence of trips the individual makes on different days, for instance. Moving to the impact on service and operations control and management, automatic vehicle location has been the key thing which enables us to identify the current positions of all vehicles and thus the deviations from the service and operations plan. And finally, the impact on customer information. Automatic vehicle location systems enable us to support provide truly dynamic customer information as opposed to strict reliance on the service and operations plan. And AFC permits characterization of normal trip making at the individual level, which can support a more targeted and active dynamic customer information function. So I think we've already seen a good deal of impact of these automated data collection systems on these functions, but I would argue there are much more significant benefits lying ahead. The relationships between the functions, the real-time functions, both service operations control and management and customer information, are based on the service and operations plan on the one hand, and the automatic vehicle location data on the other hand. This is reasonable as long as the operations plan is sound. It's a reasonable approximation of what's feasible in the real world, and deviations from it are not large. But this is fundamentally, I would argue, a static model in an increasingly dynamic world, and we may not be very comfortable living with this support for real-time functions as we move into the future. If we think about the state of research or knowledge in service and operations control and management first, and then move on to customer information, we've seen significant advances in train control systems over the last 10 to 20 years, which have helped minimize the impact of routine events on operations. So the advanced train regulation systems enable us to adjust dwell times and maximum speeds on links so as the headways on the system are maintained in light of minor disturbances that might be occurring, what I call routine events. However, major disruptions, which happen in many systems still fairly frequently, are handled by individual service and operations controllers based on their judgment and experience, and I would argue there's relatively little effective decision support provided for these controllers to make these very pressurized decisions. The models that I and other academics have tended to develop to support operations control decisions have often been deterministic and fairly simplified representations of what the true objectives and constraints that the controller is actually dealing with are. These are very highly stochastic and probabilistic systems that we're dealing with, and it's often, I think, unrealistic to try and model them as deterministic. So the conclusion on this in terms of where we are is there are very substantial opportunities remaining for much better decision support to enable controllers to make these very difficult decisions under with better help from information obtained from these automated data collection systems. If we look at the state of research and knowledge in customer information, we have increasing deployment and development of next vehicle arrival time at stops and stations. These are very widely deployed in Europe. They're increasingly widely deployed in North America, and certainly they're widely deployed in Asia. We have pre-trip journey planner systems which are also widely deployed, but I would argue they have fairly limited functionality in terms of recognizing individual preferences, for instance. So we have a fairly generic approach with limited opportunity for the customer to provide their own values, if you like, in terms of getting information from the journey planner systems. The customer information has been strongly reliant on the veracity of the service and operations plan, and I would argue they've typically been fairly ineffective in dealing with major disruptions. The evolution that I see of customer information is we're moving from an operator view of the system, which I would argue is characterized as route-based. How is this individual route performing? How are vehicles operating, leaving this terminal, to a customer view, which is much more origin to destination based. I want to make this trip from this origin to this destination, and I'm really interested in customer information which helps me make this entire journey. The second aspect of evolution is from static to dynamic, from moving from reliance on the service and operations plan to the modification of that plan based on the current state of the system and the control actions that have been taken to date. The third evolution is from pre-trip and at-stop or station information to en route with reliance on mobile phones and wireless communication generally. I think an evolution that we're beginning to see but we'll see much more of is from customer information which is provided to the generic customer to targeted information which is appropriate for the particular customer who's making this request. And indeed going more from a request-based system where I have to initiate the request for information to anticipatory systems which knowing me and my traditional preferences and travel patterns can anticipate when something's happening that I should be aware of and target me with appropriate information for my unique situation. Another important evolution which I think the US has led the way in, and now is being adopted in many other parts of the world, is going from agency or operator-developed systems to apps with developers having access to real-time data feeds from the agency, but having being encouraged to develop their own applications which can then meet the market test. To try and integrate in a couple of slides some of the opportunities and the overall view of the functions and the relationship with automated data collection systems, this slide shows the key functions, offline functions of performance monitoring and service and operations planning, and the real-time functions of service management and customer information, driven by system monitoring, analysis, and prediction tools, which some of which have been developed, others of which, I think many others of which, have the potential to be developed to support these offline functions and to support the online functions. The online functions will wind up being modified through the service and operations control function, so that the supply actually provided is the interaction between the operations plan and the operations service management function. The automated data collection systems then feed back to the current system state. So this is the supply side of the interactions. On the demand side, the customer information modifies the base demand so that people can adjust their behavior to the current state of the system. And again, the ADCS systems pick up what happens on the demand side and feed that back into this central engine. This is a blow up of just the real time functions here, where we have the automated data collection systems up here being fed by ADCS that provide vehicle locations and loads, and the control center functions, which include estimation of current conditions from the monitoring data that the automated data collection systems are providing, and very importantly, prediction capabilities, so that if the controller in control center is considering taking a sort of action, these prediction modules would help provide some indication about what is likely to happen if that action is taken, and provide more effective decision support than controllers have traditionally been able to rely on. And so the control center will produce dynamic rescheduling decisions, and on the supply side, and customer information on travel paths and travel times and paths that will provide input to individuals making use of the system. So with that fairly brief, but I hope helpful review of the big picture, I'd like to get into three specific examples of how we've used some of the automated data collection systems data to develop applications in London. We've been working with Transport for London at MIT. The Transit Research Program, which I lead, has been working with Transport for London. We're now in our 8th year, and we've done a wide range of research for them, dealing with much of which deals with this question of how do we take more advantage of automatic data collection systems. So the three examples I'll give, all from London, but with much broader applicability, are the estimation of the origin-destination matrix in terms of travel patterns, the use of metrics to measure reliability for different sorts of services, and the third example is how to use ADCS data to estimate individual train loads. So the first of these is the general question of estimating the public transport origin-destination matrix. The function this supports directly is service and operations planning, but if we can do effective origin-destination matrix estimation, I would argue this will support a whole range of functions within the transit agency built on this understanding of how people are using the system. So the objective is to estimate passenger journey origin destination matrix at the network level. The network attributes that we'd be dealing with would include multimodal rail and bus journey, but bus systems. We'd be trying to link individual trip segments or journey segments into complete journeys so we can understand the true origin and the public transport system and the true destination on the public transport system for better network planning. I should acknowledge here the work that I'm going to be presenting is based on several different theses at MIT, but these have culminated in the master's thesis of Jay Gordon that was completed now about 5 months ago, which has this title here. If any of you have any questions about this, please, in addition to providing questions during the webinar, which I will try and answer at the end of the webinar, please feel free to contact me in terms of a follow-up request for information. So the basic idea of underlying OD matrix estimation is trip chaining. Again, this is an idea that's now been used fairly extensively by other researchers and other agencies, not just MIT and not just in the context of London. So the idea is if you have an automated fare collection system, the records that are produced by transactions will include the AFC card ID, the transaction type, and the transaction time. In addition to this, for transaction types that include fare payment, the transaction location, either the rail station or the bus route, which may or may not involve time matching with AVL to determine the stop at which the boarding, for instance, occurred. So the basic idea here is that if for a particular AFC card ID on a particular day we have a transaction at location A, a transaction at B, C, and D, these are chronological with time A, time B, time C, time D, we can make a reasonable inference about what the first trip segment was, TS1, by looking for the location on the route that was boarded by the passenger at location A, the location on this route that was closest to the next boarding of this customer at location B. So the search process would be to determine the closest stop or station on the route served at location A to location B, and that would be a reasonable inference about where the first trip segment ended. So it was A to a point close to B. And we'd repeat this process for the second trip segment and third trip segment to get, in this case, the three trip segments that the customer made over the course of the day. These may be all close in time, or they may be trip segment 1 may be in the morning peak period, and trip segments 2 could be in the PM peak period. Trip segment 3 could be in the evening. But the general principle that the destination of the first trip segment will be very close to the starting point for the trip segment should hold in many cases, even if there's a long elapsed time between the time of the first transaction at A and the time of the second transaction at B. So the key assumptions for destination inference to be correct are that there's no intermediate private transportation mode trip segment between consecutive public transport trip segments. Secondly, passengers will not walk long distances between trip segments. And thirdly, the last trip of a day ends at the origin of the first trip of the day. This allows us to infer what the destination for the last boarding was if we don't have a destination tap off when we get off out of the system or off the vehicle. These won't be true in all cases, but in many cases they'll be true, and as long as we can form a reasonably good picture of how many people using the system are traveling, then we can follow a process of expanding to the full origin destination matrix, which I've described in this slide here. So the first step in the method is to infer the start and end of each trip segment for individual AFC cards. So we take all the transactions on a day for a particular AFC card, order them chronologically, and use that to infer the start and end of each trip segment during the method, using the methods that I briefly described a few minutes ago. So again, this is inferring the start of each trip segment is just a question of where the location was of the tap, which may include linking the AFC transaction with the AVL data if stop location isn't part of the fair transaction record. It can be in some cases, it won't always be, and then using the destination inference of where on that route is the stop that's closest to the next boarding location or next entry fair transaction. So that's the first step. The second step is to link trip segments into complete one-way journeys. So which of these trip segments are really likely to be part of a single journey and which are separate journeys? And we can use fairly simple heuristics for making judgments which will be fairly accurate based on the length of time between the arrival at the destination of one trip segment and the subsequent boarding. If that's in the order of minutes, it's likely to be part of the same overall journey. If it's a matter of hours, then that's almost certainly a separate journey, and there was some intermediate activity rather than just interchange between vehicles or between systems between trip segment 1 and trip segment 2. So that's the second step, linking the trip segments into complete one-way journeys. The third step is to integrate individual journeys, to add individual journeys to form a seed origin-destination matrix by time period. So this will be for all of the trips and all of the AFC records that we've been able to infer journeys for. We will aggregate these, and this will give us a partial origin-destination matrix, which certainly will not describe all travel in the system, but is a representation of a travel by probably a fairly large number of people who are using the system. And typically, again, we do this by time period. We then, the final step is to expand to the full origin-destination matrix using available control totals. These might be station entries and or exits for rail systems, passenger entries and or exits by stop, trip, or period for bus, depending on what level we have aggregate data on. And again, for rail systems, if we have train load way data, that provides us with pretty effective control totals on the loads on trains during portions of their trips. So this is the basic trip chaining method that we're using for origin destination inference. We've used this in London, as I've said, where we used it before that in Chicago, and a number of other researchers in other universities have done this with other public transport systems around the world, including South America and Canada, as well as other North American systems. So these are, I think, fairly well accepted methods now for providing pretty comprehensive pictures of the way the system is being used from these AFC records. To give you an idea about where we are on the London application, we've developed an offline tool, which was a prototype tool that we developed here at MIT. London is now in the process of industrializing this, so making this a production code that can be run with whatever frequency they want in-house without any interaction with MIT. In terms of the scale of the problem, in London, we're dealing with in the order of 12 million Oyster. Oyster is the name of the TfL AFC system. It's the name of the smart card. In the order of 12 million fare transactions per day, 6 million of those which are both entry and exit, because on the rail system in London, you're required to tap out as well as tap in. On bus, you just tap in, so there are about 6 million of those entry-only transactions for bus, about 6 million combined entry and exit transactions for rail on a daily basis. So about 12 million transactions per day. Our bus origin inference rate is that about 94%. So in 94 out of every 100 cases, we can infer the origin. In other cases, we may not be able to because we have incomplete records, and so we'll still have to do some scaling just based on the origin inference. In terms of destination inference, we have destination inference rate of about 74%. That doesn't mean that all of these inferences are correct. It just means that we can make inferences for about 73% of all fare transactions. So the seed matrix is based on about 73% of all fare transactions in the London case. To give you an idea of the computation time associated with this, for the prototype code that we've developed here, it's taking about 30 minutes to run a full day of transactions in London, including processing 12 million Oyster card transactions on sort of a standard production machine. Again, this is not the industrialized tool, but what this is suggesting, it's quite practical to do this even for a network of London size in a very short period of time. So there's nothing to prevent this being run overnight or in the evening and getting results for the next day. So that's all I really wanted to say about the origin destination matrix application in London. I think this is a valuable tool for any agency to develop. I think it's no longer really research. I think it's something that is practical and can be implemented, and I think it can have tremendous value for agencies, any agency with an automatic fare collection system. The second topic I wanted to address was reliability metrics. So reliability metrics are examples of performance measures. The objective is to characterize transit service reliability more from the customer or passenger's perspective and consistently across modes. Again, the London applications include both rail and bus. In rail, we've developed applications for the Underground, which is, of course, very high-frequency service, and the Overground. The Overground is the orbital system that operates around London. It's now a complete system. It operates with lower frequencies than the Underground, and so while service frequency has been improved, and since Transport for London took over the Overground routes from central government in the last decade, significant investments and improvements have been made, but still these are relatively low frequency services compared with the Underground. We have entry and exit fare transactions from Oyster, which operates on all of the London services, and we have train tracking data for Underground and Overground. For London bus services, these are typically high-frequency services with headways of 10 minutes or less. We have entry fare transactions only, and there's an AVL system called iBus that provides automatic vehicle location data. So let me give you some examples of this. One of the examples here, the first example here is from the Overground. Again, this was fairly low frequency service relative to the Underground service, and what we're showing here is the AM peak period with the time along the x-axis, and for one of the routes, the stations along the route from Stratford to Kentish Town on the y-axis. The blue lines here are showing the timetable for movement with the dwell times and the movement times as standard time-space diagram. The red dot here is for a particular customer from the AFC transactions, the time that they entered the station. They tapped in at Stratford at 8:01. This same customer left the system at Camden Road at 8:36 was the tap out time. So that gives us the observed journey time of 35 minutes from the tap-in time to the tap-out time. We can now compare this with the schedule. So if they arrived then, they were expecting to catch this departure at 8:06, which should have arrived at 8:29, and so this gives us the actual waiting time here by comparing the actual journey time with which results in the touch out of this time with the scheduled arrival time. We can estimate the excess journey time, the difference between what actually happened and what was supposed to happen, and other measures, including the in-vehicle time, other measures to enable us to compute a whole range of measures which are appropriate for this individual, and then we can aggregate across other individuals to get an overall sense of reliability. So those are the sorts of metrics we've developed for the Overground. For high-frequency service, we've developed the concept, which was originally developed by one of my colleagues at Northeastern University, Peter Firth, of reliability buffer time. These are high-frequency service, so customers are expecting to not time their arrival to catch a specific train. So the reliability buffer time, in this plot, we're showing travel time or journey time along the x-axis, and this is the probability density function with percentage of journeys or probability of journey time along the y-axis. And so for a particular origin-destination pair, this distribution is showing the distribution of journey times or travel times. If we take the difference between the median travel time, the 50th percentile, and some measure of the upper tail of the distribution, in this case the 95th percentile, we can define the reliability buffer time as the difference, say, between the 95th percentile and the median time, and this would be the additional time a passenger must budget to arrive on time for most of the times they make this journey, say 95% of the time. So this concept of reliability buffer time is one that we think is very important for capturing service reliability on high frequency routes. In terms of the applications of this, I'm showing you one application for the Victoria line, one of the major underground lines in London. This was from the AM peak in 2007, and what we're showing here are two data points, northbound and southbound, for February of that year for the AM peak, and two corresponding data points for November of that year for northbound and southbound. This shows the total excess reliability buffer time. So some reliability buffer time might be expected because of the normal service process of 4-minute headway. So people arrive randomly, they have to wait for the first train. So the excess reliability buffer time is the time you have to allow over and above what would normally be associated with random passenger arrivals. The red part of this, so this says the excess reliability buffer time was about 5 3/4 minutes northbound, or 10 3/4 minutes southbound in February. It was 6.5 minutes northbound in November and 7.38 minutes southbound in November. The red part of this is sort of the baseline reliability buffer time. This is the recurrent time that is not affected by external events like weather. February of that year was a bad weather month, and so there are a lot of incidents related to ice and snow and bad weather conditions. November was a much better weather month, and so you didn't have that. So the red portion is the baseline reliability buffer time, and the excess reliability buffer time is the time that over and above that you're incurring because of the external conditions that were affecting operations. So this is the notion of excess reliability buffer time in the underground example. And finally, in this reliability metrics case, looking at bus, in this case the challenges compared with rail are we don't have any tap off, we just have the tap on, and the tap on occurs after the waiting time at the stop. You don't tap when you get to the stop, you tap when you get onto the bus, but the wait is an important part of the journey time, and we want to include that in our measures. So the strategy to use is to use trip chaining to infer the destination for all possible boardings, as we just described, and use automatic vehicle location, or in the London case, iBus, to infer what the average passenger waiting time based on random passenger arrival process, or what the appropriate passenger arrival process is, and the actual in-vehicle time. So that's the reliability metrics. The final topic I wanted to discuss briefly was our attempts to estimate individual train loads in the Underground case. The function here, looking at it as an offline function, this would support service and operations planning and performance measurement. So the idea is how many people on a specific train at a particular point in its journey. Ultimately, I think we would like to be able to estimate this in real time. That could inform improved customer information and improve operations control decisions, but we're not at that point yet. So the objective then is to estimate the passenger load for each train at each station. Application to the Underground. The data is the Oyster data we've already talked about, and the train tracking data in the Underground. This is called NetMIS, which provides train arrival and departure times at stations. So why is this important? Well, passenger load measures passengers will infer the quality of their trip based on whether they're seated or standing, based on if they're standing, on the density of standees, how crowded are they, and on their ability or willingness to board a vehicle. So all of passenger loading on a vehicle at a particular station affects all of these things, and so it would be very valuable to estimate this if we could. But these are generally not available. Passenger load is generally not available for most automated data collection systems. The challenges in the London case, the Oyster times for the system which we were using, and this work was done now 2-3 years ago, were truncated to the minute, so entry and exit times have errors of up to 59 seconds. So in terms of what the time the passenger is actually on the platform ready to catch a train, we might have errors of up to 59 seconds, and similarly at the other end in terms of what train they arrived on. The train tracking NetMIS data is incomplete. London has a large number of lines. A lot of the infrastructure is quite old, and despite extensive capital investments, the train tracking data is not seamless and complete. In-station access, egress, and interchange times are variable across stations, individuals, and instances. Capacity constraints can be binding and are variable. At what point will someone decide the train is too crowded that they don't want to try and get on board, and they'll just stand back and wait for the next train? And some origin-destination pairs have multiple paths available, and actual path chosen is unknown. This gives you an idea of this. This is the central zone in London, just the Underground lines, and you can see that for many origin-destination pairs, for many journeys in central London, there are multiple paths that might be equally plausible. So the definition of an itinerary here is a feasible sequence of trains for a passenger journey starting at one station at one time and ending at the other station at the other time. So the proposed methodology is to categorize the observed passenger journey as either a single path or multiple path trip, and whether you have a single itinerary or multiple itineraries available for that trip based on the NetMIS data. To select the most likely path for each of the multiple path cases, and to select the most likely itinerary for each multiple itinerary case, assign passengers and compare assigned flows with train capacities. The model exploration that we did now again a couple of years ago is to look at this subset of all passengers. The simplest case is A, which is about 1/3 of all passengers. We have no interchange. The capacity is not binding because of the time of day they're traveling, and there's only a single path. That's the cleanest case. About 1 in 3 passengers are this. And then we can look at these other cases to understand how well we can make inferences where the situation is less clear. The conclusions on this, I'm not going to go into any details. Again, there's a thesis done by Liz Paul on this, which I can provide to anyone who would like it after the seminar. The conclusion, though, is inferring train loads on the Underground is not yet feasible offline. Main reasons: missing net miss data. Only 3 of the 11 underground lines have complete train tracking data. The Oyster timestamp truncation problem I mentioned, and clock misalignment between stations. This problem is in the process of being dealt with. This has been dealt with, and this will take a longer time to deal with. However, the basic groundwork for tackling the offline problem has been laid, and generation of itineraries works quite well in terms of analyzing a fairly complex network. So the keys to improving results for this are improved modeling of access and egress times and improved path choice models. The future research, in now wrapping this up, before I take questions and discussion, to develop better models to support service and operational control and management and the customer information functions, both descriptive models, predictive models, and normative models, which will be actually suggesting what actions a controller might take in a certain case, rather than just describing the system or providing a predictive capability about what would happen if the controller made a certain decision. And to evaluate the marginal costs and benefits for additional data availability in real time, notably AFC data and APC data. What would be the value of providing that data off the vehicle in real time? Okay, I've now finished the presentation, so what I will be doing is putting up my interaction screen here, and I will start looking at the slides now, at your questions. So first question is, can we get a copy of the slides? And the answer is yes, we will provide copies of the slides. How do you recognize the transfers from AFC data was the second question. And what we do there is we look at the time of the alighting from the first trip segment. Let me just go back to the case here that I was describing. Okay, so if you can see this, so the question is, how do you recognize transfers from AFC data? So the first trip segment ended at a point close to B. The second trip segment ended at B. So we look at the inferred location of the alighting at the end of trip segment 1, and the inferred and the recorded location of the boarding at B in terms of the location and time, and we use heuristics to say, was it reasonable? One, was it reasonable that that there was no activity at this interchange point? If there was, and that will depend on the headway of the route being boarded at B. So if this is a low frequency service at that being boarded at B, then it might be reasonable for a waiting time if the individual was unlucky and arrived at the stop B, say 45 minutes before he boarded the service at stop B. That may be because there wasn't any intermediate vehicle that arrived before that. If, on the other hand, so we might we look at the elapsed time, look at it in the context of the headway, and make a judgment about whether it was reasonable that there was no activity at that, no non-travel related activity at that interchange point. And if that's the case, then we would link those trips as part of a linked journey. I'm just going back to the questions here. So yes, we will provide links to the to this material so you can access it directly. I was wondering if the AFC type of AD systems is the most suitable method for OD matrix estimation. So as long as we have an AFC system that allows us to uniquely identify the card on which the transaction was made, so we need to know who the user was for all transactions by an individual in that day, and as long as we have the data on the location and the time of each transaction, then a whole range of AFC systems could be appropriate for inferring linked journeys. Yeah, so the next question is, again, how much time is there between trip segments, and have you accounted for people who run errands, such as groceries or dropping off kids? Yeah, so that's part of the question about under what conditions do you assume that the individual was not doing anything which is non-travel related at this interchange point. There's a gray line here, obviously. Clearly, if you're dropping off kids, that's an activity which is non-travel related. It was an input to your trip chaining decision, so it's important to understand that there was an activity there, and so even if you'd improve the network to allow someone to not visit B on route from their initial origin A to their final destination, in this case C, for instance, that would not be of interest to the customer because there was a non-travel related activity at location B. So we use heuristics to make that judgment. In terms of confirming that the judgments we've made are realistic, the way we've done this in London is to compare the number of journey segments or trip segments that we're getting from our inference scheme with survey results to make sure that they're consistent with that. Next question is, has TfL utilized the new origin destination matrix to redesign their network? The answer on that one is that, as I said, Transport for London is now industrializing this ODX, as we call it, OD, and then expansion tool for the network. So they're very committed to using it. One of the things they've done immediately is not do their traditional bus survey procedure, because they believe they can get the information they need more reliably and certainly at lower cost from this ODX tool. I don't believe that they have got to the point of redesigning the network. That's a function that was supported by their manual data collection systems and now will be supported by the ODX tool, and so it's sort of a separate question about how they do that. But I don't believe, the direct answer, I don't believe they've done that yet. Okay, next question. So the passengers have to tap on again. So again, with bus networks in London, as in London or most of North America, for instance, you tap only when you get on and you don't tap when you get off. But every trip segment is an individual vehicle trip, travel on an individual vehicle, as opposed to many rail systems where you have no fare transactions between alighting one train and boarding another train at a particular interchange station. That's typically the case in London and typically the case around the world. So in London, you do not know exactly what path the individual took just from where they tap on and where they tap out. You may be able to make some inferences based on the journey time, but still you don't know exactly what transfers or interchanges they made behind the gate lines. And so that's why the issue of route choice or path choice in the underground network or any rail networks is still a very, very important question that is not fully answered by this information. So that's the question that. So again, in the London Underground system, transfers are free. It's based on the origin destination as well as the route you took. but again, we don't know the path choice within the underground between the tap in and the tap out. So again, the next question here is, following on the current discussion, what if the whole journey is within the rail system only, tap in card at the entrance, tap out the card at the exit? How can we further transfer point? Yeah, so this is the path choice or route choice question, and it's one that you still need to have additional information on to infer. So the work we've done on path choice in London, the traditional methods that the Underground has used for path choice has been to rely on what they call a rolling origin destination survey, which asks individuals the route they took and then scales that up, expands that to represent percentage probability of different paths being selected between each origin destination pair. So those are the methods that we've used, that they've used. We've, using that same RODS data, we have estimated path choice models. A student who's now a faculty member at New York University did this. Jean Guo is his name. It was a doctoral dissertation about 5 years ago. Juan Carlos Munoz has a student at Católica who's doing similar work in the Santiago metro system, Sebastian Ravo, and so there are a range of methods which are possible for doing this, which have been applied. Okay, so Jay Gordon said says he's posted his email. You've seen that already. Question is, what do you envision the role of APC data in light of increasing tap-on AFC data adoption of us? This is by Rabi. Yeah, this is a very good question. I think if you have a good AFC system, it's a somewhat weaker case for investing heavily in APC systems. However, you do have the issue in the ODX of expanding the seed matrix to represent this last step here, to expand the full origin destination matrix using available control totals. And this is where APC data can still be of great value. This issue of expansion, whether it's going from 73%, as the case in London, to 100% of all trips, or whatever it is, there's still going to be some expansion and scaling needed, and the control totals are very important, and APC data can be very, very helpful there. Next question was, is the Oyster card system the only payment method available in London? No, it's the dominant means, but people can pay with magnetic stripe cards as well, and so Oyster does not represent all trips, and so scaling will certainly be necessary. And that's again part of the scaling part of the process. So we have to make sure, have to satisfy ourselves that there isn't any bias represented in the Oyster subset of data. Again, because Oyster represents 85 to 90% of all journeys in London, we're confident there's no bias there. But in other cases, we'd have to make sure that the AFC subset is a representative sample of all users, so we can do the scaling appropriately. Okay, how do you deal with questions with the non-Oyster trips? I think I've mentioned that through scaling. Next question was, is it useful to develop an automatic travel information system without having timetables and just to focus on real-time tracking of the system fleet? Yes, I think that can be quite useful for high-frequency services. You still have all of the network and route journey planning functions that that you have to support. But in terms of real-time customer information for people making their trips, I think you don't really need to have the timetable information readily accessible on high-frequency services. Next question is, what are the barriers to real-time APC data? It depends what sort of data you're talking about. Again, I was in Hong Kong earlier this week. As I mentioned, we've just started a new research relationship at MIT with MTR in Hong Kong. And the issue of providing train way data in real time off the vehicle was one that that they're thinking about and beginning to explore. And I think that could be quite valuable in terms of getting an estimate on of the load onboard trains at particular points in real time, so you can make better operations control decisions. In terms of APC data, in terms of passenger count information, there's a question about which agencies are closest to implementing that. I'm not aware of any agencies that are very close to implementing that in real time now. Next question is, what would be the ideal time truncation for Oyster data? They're new readers which they're now completely installed, I believe, on the bus network and are in the process of installing on the underground network, will give precision to the level of the second, which is certainly adequate. So yes, so a minute is clearly too coarse to be able to estimate reliably when each customer got to the platform to board the train, but second level data would be absolutely fine for that. Next question is, you mentioned that you use surveys to verify your research. What kind of surveys do you use? These are surveys that are done in the case of London, route surveys that they've been doing for for a length of time. The survey that we're using to try and get confirmation of our journey linking and overall ODX procedure is the London travel demand survey, which is conducted on a rolling basis for a sample of residents in London. We're using that data also to on another research project to get some idea about the differences in reported travel versus recorded travel by the Oyster card journeys for the Oyster card held by that customer. So that's research that's being done currently by Laura Regal, which should be finished up this spring. The other surveys were the Rolling Origin Destination Survey, which is conducted by the London Underground, and the similar survey on buses, which was the Bus Origin Destination Survey that's now been replaced by the ODX tool. Another question, I'd like to have the presentation if possible, and I think that's it. So thank you all very much, and I hope you've enjoyed it.